Today we have our newest fellow presenting, Abel Jansma, and he will talk about his past and current work and fellowship from macro to micro with modules. Thanks, Abel.
Yes, thanks for the invite, which I sent out myself. So I'm the new Deep Fellow, and I'll present today a bit of the research direction I've started in the last year and will continue here for the coming period. And it has to do with the relationship between macro and micro and something called Möbius inversion. And the word that ties it together is Mereology, and I hope to make clear what that means during the presentation. The first thing I want you to look at is these kinds of knots. They're called Brownian links, and they have a special property, namely they are connected. You cannot pull these rings apart. However, if you leave one of them out, the whole thing falls apart. They're no longer connected. So they're sort of linked only as a group. There's not, for example, this one, none of the pairs are actually linked. You can see that like the blue one is everywhere in front of the orange one, for example. However, they are linked as a triplet. So sort of they are higher order linked. And you can do this for any number, actually. So this is 3, this is 4 links, that's 6 links. And especially the 6 link one, you can see that you can easily generalize this to all integers. But what's crucial is that this higher order idea, that these are only higher order connected, is relative to a decomposition. So it's only higher if you say that the natural way to decompose these 3 rings is into 3 rings, rather than saying this is a unit that's just connected. And this sort of vague intuition that it's a decomposition that determines if it's higher order or not. That's what I aim to make precise and useful today, so that you can really use this to study complex systems in more general ways.
Sorry, on your first slide. You say it's dependent on decomposition, but whatever decomposition I make of these objects, they always fall apart.
So by decomposition, I mean sort of your way to describe it. So this is sort of very special if you want to consider these 3 separate rings.
But if I consider it as a group of 1 ring and a group of 2 rings, then it still holds.
That's right, but not if you consider it as 1 unit of 3.
No.
Exactly. So but we'll make this much more precise, what I mean by decompositions, and yeah, I hope that's exactly what should become precise.
Okay.
So the overview of what I'll talk about is first exactly this. Like, what do I mean by decomposing complex system, and what does this word Mereology have to do with it? And then I'll show that you can do something like calculus on these Mereologies, on these decompositions. And particularly what we'll look at is something called incidence algebras and Möbius inversions. And then to convince you that this is a good idea, I need to do 2 things. The first is show you with a lot of examples that this reproduces well-known quantities. So I'll show some examples from information theory, biology, physics, and game theory. But the second thing I have to do is to show you that you can do new things with it. So I'll show some new applications that I've come across, which is a better way to decompose information, decomposing KL divergence and causal effects, as well as like this slogan at the bottom should not make any sense yet, but I hope it will make sense. Namely, renormalized couplings are Möbius inversions over a Galois connection. That's something that only makes sense in this context, and I hope that at the very end, we'll have a look at that. Right, so part 1, decomposing complex systems. So I'll start with a very simple example to sort of show the kinds of reasoning we'll do. So say you have the height of a person, and we're assuming that it's determined by 3 genetic variants, G1, G2, and G3. Then I'm going to say, okay, well, the height of a person with these 3 genetic variants can have contributions from each single one of them, which is just this sum. Okay, this is very boring, right? This is saying that these just add up, there's no interactions. Biology is more exciting. So maybe what you should be doing is saying, well, actually, I'm going to decompose this not into these individual genes, but into the power set of genes. I'm going to take the set of genes, generate a set of all subsets, and decompose it over that. Actually, exactly. Those 2 have to also be there. You get a 3 point and a sort of 0 point. And this is already an indication of how these interactions that are allowed by your model emerge from your chosen decomposition. So this whole notion of pairwise and triplet interactions are sort of captured by the assumption that this height decomposes into a power set. So let's now make this more general, rather than the specific example of height. Let's say you have some quantity Q of a system S, and you want to write it as some decomposition over S. I'm going to write big Q as a sum of little q's. And that's because I consider this big Q to be sort of a macroscopic thing you could measure, which is an aggregate of many microscopic things, contributions of all the parts. And this is still just a sum, which you might worry about is too simple an assumption here, but you can hide a lot of complexity into this decomposition. It's basically analogous to shooting a complicated design matrix when you're just doing linear regression. So rather than doing something more complex than linear regression, you can also just start adding like x squared and cosine of x into your linear regression problem and regress it linearly against those. That's somehow analogous to how you can come up with more complicated decompositions here. And then the forward problem of science is, given sort of the microscopic quantities here, predict the macroscopic, which is sort of a standard thing to do. But there's also the inverse problem, where you say, I can only do measurements on the macroscopic degrees of freedom, and I'm going to use this to infer these microscopic ones. And what I will show today is that you can solve this inverse problem, going from microscopic observations to microscopic theories, by exploiting a structure of this decomposition. In particular, I will show that if there's like a hierarchy of parts in your system, that this has a certain structure on this decomposition, namely a partial order. And what is a partial order? Right, so I'll define it here precisely. A partial order on a set is just a binary relation on that set that has three properties. It's reflexive, transitive, and antisymmetric. It's basically anything you would expect of an ordering relationship. On top of that, it says not every two elements have to be comparable. Some of them can be neither smaller or bigger than the other. And sort of the canonical example of this is the power set, where you say, I'm going to take some set, generate all subsets, and I'm going to order these subsets by inclusion, so that A is smaller than B if A is included in B. And here's a picture of what this looks like for 2, 3, and 4 variables. And you get sort of these hypercubes of orders, where order goes from the bottom, which is the smallest element, the empty set, to the top, which is the full set. And in between, you have all the intermediate sets, some of which are not comparable, like the set 0 or the set 1. You cannot compare these. None is contained in the other. And there's other examples. You can order partitions in a similar way. So again, take a set of 2, 3, or 4 variables. Consider the set of all partitions you can make of that set. And these have a natural ordering, which is called by refinement. So you have the finest partition at the bottom, which is just the set that contains all singletons, and the coarsest at the top, which is just a full set. And in between, you have sort of finer and finer partitions.
Can I answer the silly question? It sounds very much like a combinatorial type of analysis. Is that very similar?
So all these ideas are mainly used in combinatorics. Yeah, and a lot of the theory I'll use today started in combinatorics, so people interested in just basic combinatorics and number theory, actually. So now I'll come to this word mereology. So it's a well-established word, but mainly in sort of mathematical logic and philosophy. And it comes from meros, which is part, which you might know from polymer, a many part. It's the study of parts, the relationship between parts and poles. But I will make a precise definition of it now that I think captures exactly this. And if there's no philosophers in the room, I hope you agree with me that this is a sensible thing. I will say a mereology, denoted D of S, is a mereology on a system, S. And what it is, it's just a locally finite, co-rooted poset that has S at the top. Now, what do these words mean? Locally finite means that any interval on the partial order is finite. In particular, any finite partial order is locally finite. But in fact, you only need intervals to be finite. And co-rooted just means that the partial order has a unique largest element. So an example of this would here on the right. This is a mereology on a bicycle, where at the very top, the unique largest element, which is required to be there by the co-rooted property, is the full bicycle. And as you go down, you go to finer and finer parts of the bicycle with the empty bicycle at the bottom. But there's a parthood implied here. For example, here in the middle, you have the wheels. But you can see that both the spokes and the tires are part of the wheels, but the frame is not. So this sort of partial order captures really parthood relationships. And for example, if A is a part of B and B is a part of C, then A is a part of C. Is that?
What do you mean by finite here? In what sense?
So this is a set.
Yes, the interval A B is a set.
Exactly, and the set is supposed to have a finite number of elements.
A finite number of elements.
Yes.
So X is definitely not real value.
It's not continuous, basically.
It's not continuous.
Exactly, but actually, it could be that the partial order has infinite elements, but every element is finite. For example, the natural numbers, ordered by their usual ordering, is an infinite partial order, but the interval between any two natural numbers is finite.
Okay, so natural numbers would work, but real numbers cannot.
Exactly. Yeah.
No, right, largest element.
No, so it's not a Mereology,
Yeah.
but it is a partial order. Exactly. That's an important difference. And for mathematicians, you might feel like this is kind of similar to a topology. And it's indeed true that every finite topology is a Mereology if you order the open sets by inclusion. But Mereology is more general. So this doesn't have to be closed under intersections or unions. In fact, intersections or unions don't have to be defined on elements at all. But the reason I'm interested in this is because we were looking at these decompositions over parts. And if we have a Mereology on our system, then we can rewrite the decomposition as a sum over the partial order. And that doesn't make sense that that's useful now, but it will turn out that that's extremely useful. Because you can do something like a calculus on it as soon as you can do it. So I'll look at some kind of calculus on partial orders or on Mereology.
What do you mean by sum over a partial order?
I mean, this. That the sum goes over all elements t smaller than s, and smaller than is defined by the partial order.
But S is your top element.
That's right.
So you're still summing over everything.
Indeed, but s could be also another element. So this will be true for any element. I'll get to. That's important that you can do this for other elements as well, and I'll show precisely why that's important.
But this is like a level set now. Then.
Basically. No, it's not. It's not all the elements at a certain level. It's like an upset
Lower than
or a downset. Yeah.
Lower than a level.
Yeah. Exactly.
So to be clear, so if you take the set on the right, you just sum of all elements.
Yeah, but if you would observe the big Q on the tires or on the wheels, then you would get contributions from the spokes and the tires and the empty bike, but not from the frame.
Exactly.
So you're summing down.
But all the ones that are included in this big S.
Of course.
Yeah.
Okay.
Yeah, if you observe on big S.
Yeah.
So what we see now is that these decompositions, they involve functions on partial orders, right? Big Q and little q are functions on the partial order. So we should understand what kind of structure these functions have. And in particular, with this set of functions that exploit the structure of a partial order, they form what's called an incidence algebra. And it's a triplet of three things, namely one locally finite poset. I say poset, I mean partially ordered set. A vector space of functions. And these functions, they don't just go from the poset to the real numbers or to a field. They go from two copies of the poset because they use intervals. And intervals needs two elements. But if you just look at a function from the poset, then you don't exploit the ordering. So you need sort of to look at intervals here. And crucially, what makes this into an interesting algebra is that you can define a multiplication on these functions that's convolution over the partial order. So the star multiplication of two functions in the incidence algebra evaluated on two elements. Oh God. This is you.
No.
I'm still in.
Zoom, click zoom. Below.
Right. Exactly.
And double click on the screen. Yeah.
There we go.
Okay.
Good.
So what happened?
So you can define this star multiplication and multiplying two functions with this star, evaluating them on an interval, convolves these two functions over all intermediate values. Okay, whatever, you can define this. But there's some special elements in this algebra that turn out to be very useful. Perhaps the most boring one you can imagine is the delta function, which just outputs 1 if the interval is trivial and 0 otherwise.
This could be like a path integral, like start point A and B and go through all the paths that go.
Exactly. So yeah, this is why I'm starting to use this word calculus, because we'll slowly move towards something like that. For example, you have this zeta function here, which outputs 1 whenever A is smaller than B. So it sort of captures all ordering relationships in the partial order. And then here they are, and they have special properties, these two, namely delta is the multiplicative unit of this star multiplication. And zeta is exactly what you say. It's like an integrator over this partial order. So if you multiply zeta with any function of the incidence algebra, that's basically like integrating that function over the interval you've provided. Now, this function only has one argument here. That's because I consider it to be sort of independent of the second argument here, so that this looks like normal integration. But it's, of course, holds in more general. But an immediate question you might now have is, does zeta have a star inverse that sort of undoes integration? Because that would be something like a differential operator on this partial order. And it turns out it does. So the inverse of zeta, inverse with respect to this multiplication, being that they multiply towards the delta function, that's called the Möbius function. And that's a special thing. It has sort of a quirky definition, which you actually don't need to worry about too much. It's 1 on the trivial interval, and on any other interval, it's recursively calculated. So it's not trivial to calculate like this, but it turns out there's some nice ways to do it. The definition is not too important. What's important is this Möbius inversion theorem that follows from it. Maybe it says that if you have a locally finite poset P with a function f, then the following two are equivalent. Namely, f being some kind of integral over the partial order is equivalent to invert. You can invert that sum and write g as a sum over the partial order of f, as long as you weigh the values of f by this Möbius function. So if you imagine that actually summing over the partial order is multiplication with zeta, then this looks very natural, because then you see that zeta and mu sort of do the opposite thing. But in this formulation, it's much more clear why this sort of undoes integration. And for us, this means that not only can sums over partial orders be inverted, in particular, you can do this over Mereology. So going back to our notation with big Q and little q, you can do this. You can solve this inverse problem in two situations. Namely, the first thing you need is that you have to know this Möbius function. Because you don't want to be calculating it recursively. You want to sort of exploit the structure of your Mereology so that you can actually efficiently calculate it. And two, and this comes back to your question, Christian, you have to be able to observe big Q on the whole Mereology. So you see that here, right? So you have to suddenly measure this big Q on the whole Mereology. Once you know all these values, you can estimate little q. Now let's go back to the example we looked at before, height. I will only consider 2 genetic variants now. Let's see how this works in practice. I'm going to say the height of a person decomposes over the power set of 2 genetic variants. You have these 4 contributions. Now big Q, which is height, can be evaluated on all 4 elements here. And you get different values. In this case, they all become taller and taller as more mutations that you get. And then because combinatorics people and number theory people have thought about Möbius functions for ages, they have calculated all these Möbius functions for us. For example, on the power set decomposition, we know that it's just an alternating sign that depends on the size of these 2 sets. So you can immediately fill this in now and get an expression for the effect of a single genetic variant. And what it is just the height of a person with that variant minus the height of a person without that variant. Very boring. That's what you would hope it reduces to. You see, it does look a bit like a differential operator. This sort of makes sense. It's slightly less trivial for the case of the interaction between 2 genetic variants. There you see, okay, yeah, we get this alternating sign where you have to sort of add the height of people without genetic variants. But visually, that makes a lot of sense here in the bottom right. So you have sort of the height of a person with both genetic variants, then you subtract these two, but you've subtracted the gray area twice now. So you have to add it back once to get the orange area.
It's like all characters kind of thing.
Yeah, this is, so on the power set, actually, this reduces to the inclusion-exclusion principle. And it's related in a much more general sense to Euler characteristics. Vastly more general. We can talk about that later, actually. And this is why I call this like a calculus of Mereology, because you can somehow do integration and differentiation on these partial orders now. And they reduce sort of the natural idea of interactions. Yeah.
I'm actually a bit confused. I mean, so normally if you do a summation or an integral, you can only do it one way, no? I mean, so I don't. So the inverse problem is usually ill-defined,
Right.
Because you integrate out degrees of freedom or whatever.
Right.
So you lose information.
Yeah.
And somehow you say, no, this is not a problem because I can just invert it and retain all information. This sounds.
Well, we're doing it in a non-continuous setting, right? Like differentiation is just like differences, and integration
So
is sum.
It's really the analogous to integration and differentiation. This is how you think about it.
That's how I think about it. Yeah, but in a very discrete setting where calculus is kind of boring.
Okay, then I'll.
Yeah, this is not true for normal calculus, of course. No. So now we get to the point where I'm going to show you that this is sensible. By showing you that this occurs over and over throughout the sciences, and it leads to well-known and important quantities if you actually do this procedure. So just to summarize, the name of the game is choose some microscopic thing you want to decompose, then choose a Mereology that you think is appropriate for these kinds of systems or quantities, and then derive the microscopic theory, these little cubes, by inverting it. First example from information theory. What's the most basic thing we can start with? Consider the entropy of a set of variables. Just Shannon entropy. And let's assume that information is somehow built out of contributions from all possible subsets of variables. So maybe we have 10 variables, but all possible subsets could add a little bit of information to the overall aggregate. So let's impose this power set Mereology. Well, we do that. We say it's a sum over some quantity that I suggestively call I here. Of contributions from all subsets. Well, let's invert to figure out what these contributions actually are. And we can do that. We can do that because we know the Möbius function. It's just this power set one. And you can write it out. And what do you see? Suddenly there's mutual information there. And you can put in the Shannon information, and then you get just sort of your famous definition of mutual information. So a way to summarize this is that mutual information is the power set Möbius inverse of entropy. And it's uniquely so. So this inversion is unique. So if you have Shannon information and you think that variables can come together in all possible ways, then the unique Möbius inverse, the unique microscopic theory associated to entropy is mutual information. And you can do the same for pointwise quantities. So if you don't take an expectation value, but you take a surprisal here, you get pointwise mutual information.
If it this second equation also the interaction information,
So exactly. So now I've only written it for two variables here. You might ask, how do we generalize this to more variables? And there's sort of two ways to do this. You have this interaction information, which says indeed we're going to continue doing the power set. So for three variables that look like this, and then you'll find this, which is known as the interaction information. And you can generalize this to any number by always taking the power set. But there's a different way to do it, namely the total correlation, where you say actually mutual information is the KL divergence between the joint and the product of the marginals. So let's continue that pattern and say, okay, total correlation of three variables is just this thing. But that corresponds to assuming a different Mereology in this case. So you can sort of see that actually as soon as you impose a different Mereology, you derive a different generalization. But both reduce to the standard mutual information if you go to one variable fewer. So you see here, instead of arguing about what is a more natural equation, you can also argue about what is a more natural decomposition of your system. Sometimes it might be this, sometimes it might be this, depending on how actually the variables.
So it depends on the joint of Mereology, you get different information.
Yeah. Yeah.
Do I understand correctly that it means that your decomposition in mereology is not unique?
It's unique.
It's unique.
Yeah, given the mereology
Yeah.
and your microscopic quantity, entropy in this case, the inverse is unique.
We have to choose beforehand the other composition.
Yeah, so that's the name of the game. Choose a big Q and choose a mereology, then you're done. The rest is fixed.
But it sounds like you also choose small q by saying it should be this log function. Because you plug this.
No, so this log, these are all big Qs, right? We assume that the big Q is Shannon information.
Yeah.
So let's go.
Back to the previous.
Yeah, exactly.
So we're interested in.
So I don't assume that this H has a log shape. So actually, if you don't know what Shannon information is, you can still write down this definition of mutual information.
Yeah.
But if you then realize actually what I'm looking at is Shannon information, then you can plug that in and get this.
Yeah, but then so but it means you still assume something about the microscopic level by saying it is Shannon entropy.
That's right. So if you change this entropy, you'll get different notions of these i's.
So what I mean is that so this function, this I as a function of x and y this is always true.
Yes.
But if you now want to get something, I'm not sure if useful is the right word or not.
Mhm.
You want to get the second equation, then you have to assume something extra. And this is not something you.
That's right. Yeah, you have to. So exactly. That's why. So fixing Q fixes the microscope. So if you fix Q to H of S, then you get this one. If you fix Q to this, then you get this.
Yes.
That's right. Yeah. But so, to be honest, I find this the more interesting equation.
Yeah, sure.
Yeah, that's true. We can argue about.
But I have a similar question, but then on the next slide.
Oh, yeah.
It's two different.
Mhm.
So I understand that if you choose your mereology, then you get this expression.
Mhm.
But what I don't understand is where does this mereology comes from?
From your brain, right? So it's not I've solved science now. The point is that rather than arguing about equations, you can also argue about mereologies.
So you have to come with the best partition of your system that you think is the best.
Or try different ones and say, okay, relative to this decomposition, I find these interactions. To this decomposition, I find these interactions. There's something to be said for either. Maybe you want to create a model that minimizes higher order interactions. Then you search through mereologies, which one's your favorite one. I mean, there's still a game to play here.
Yeah, because it's not clear what the difference is, right? I mean, if I look at these two, okay, one
Mhm.
more complicated than the other. So how do I interpret it? You actually have this layer of x, y, example.
Well, here you're implicitly saying, I think that variables can come together to carry information in pairs. Here you're saying, I think that's not possible.
Okay, so it's some causal inference stuff.
Yeah, for example, you can do something like that. And then choose the simplest mereology consistent with your causal structure. Something like that, for example.
And are there other mereologies for information, or these are the only?
We'll come to other ones later. You can go much more complex than these. So these are sort of the simplest thing you could imagine, but you can go much more complex. But I'll come to that in a second.
Somehow by setting the mereology, you can predict new definitions of information.
Yeah. Good. An example from biology, we've kind of seen this one because this is just generalization of this example of height, where you say, okay, I have some phenotype that I'm going to decompose over a genotype. And if you assume that they decompose over the power set again, then you get this description of basically what we did with height before. You get some, for example, for the 3-point interaction among genes here, you get some long expression, which, okay, whatever. The nice thing is that it turns out that this is used in biology a lot. Although they usually use much more complicated arguing to arrive at an expression like this. Sometimes they use geometric intuitions of fitness landscapes, but actually it's sort of the only reasonable thing if all genes can carry effects. So by now this should be boring because we keep doing the same trick. I'm going to do it again now in physics. Let's look at the Ising model, our favorite thing. Standard Boltzmann distribution. Only peculiar thing is I will assume that we're in the 0-1 basis. So spins are not negative or +1, they're 0 or 1. And instead of only nearest neighbor interactions, I'm saying there could be interactions at any order. Then one thing to note is that if we're in the 0-1 basis, there's sort of a nice property that the energy of any state where a subset T of the spins is turned on is just the sum of interactions, of couplings, of all subsets of T. That kind of makes sense. But that's exciting because now we again have sort of a thing we can Möbius invert because we have a sum over subsets. So we do that and we get an expression for the couplings of an Ising model in terms of log probabilities again, or energies in this case. So to clear this notation up a bit, I'm going to, for the probability of Si being A, Sj being B, and the rest being 0, I'm just going to write PAB to simplify notation a lot. And then you can solve the inverse problem with these two expressions. For example. And you can do this for any order, of course, but I've only shown it for orders 2 and 3 here. So if you have a lot of data from which you can estimate probabilities of states, then you can sort of immediately solve the inverse Ising problem like this. In the 0-1 basis. If you want to do it in the -1 + 1 basis, you would have to transform your couplings, but also that seems doable.
Sorry, is it kind of a, okay, what's known as Boltzmann inversion, something like that?
I don't know that. That sounds interesting. I've never heard that word before. Boltzmann inversion?
Well, it's the same thing. As you measure the Boltzmann distribution,
Uh-huh.
and then you actually invert it to get the interaction energy, right?
Okay.
I mean, this is, it sounds, now,
That's
okay.
a more two-body.
Yeah,
distribution,
well,
so it's
okay,
more
well,
approximate than.
yeah, but this also sounds like a two-body approximation, right? The first one.
This is the pairwise coupling. This is the triplet coupling. You can do this for any. Yeah.
It's not the same thing because in one case is a fitting and in this case is a exact inversion. You can do this if your system is complete.
Yeah. So that's why I assume that all interactions exist. Then you can do this Möbius inversion for all couplings. And this is actually used a lot. Sorry?
I'm not sure if you're going to experiments or not. That's for example, so if I have my some sort of real Ising experiment, Ising model experiment, and one physicist argues only nearest neighbor interaction are important, one physicist argues
Right.
second and third interactions were also very important. Can you then use some sort of this inversion methods to devise a...
Yeah, so this is assuming all couplings exist, and then you can still later empirically find out only this one is non-zero, all the other ones are 0.
Yeah, but
That could happen. But you can also implement this assumption in your Mereology.
Yeah.
That's something I've been thinking about, and I don't know exactly yet how useful that is. But it's something I definitely was thinking about. Yeah.
But it's always a big question. I mean, how far do you need to go in your
Yeah.
interaction?
Yeah, absolutely.
If you could use your method to say, well, you can now at least experimentally sort of devise a test that would be, yeah.
Absolutely, yeah.
Yeah.
So yeah, one thing to say is that this is also used a lot, actually, this formulation, although it wasn't really originally seen through this lens. The first time I was sort of approached from this direction was actually at my last deep seminar a few years ago, which I had no idea about Möbius inversions back then, but this is what started this whole project, seeing that you can solve the inverse Ising problem like this. Okay, that's the Ising model, which we love, but what if you can actually not measure these energies, because they might be hard to measure? Maybe the only thing you can measure is correlation functions, which is often what we assume. Then we have objects like this that we have access to. If you now impose the power set Mereology, you just get central moments of your variables, which is kind of boring. More interesting is to impose the partition Mereology. Finally, different Mereology. Also for that, our combinatorics colleagues have kindly calculated the Möbius function already. It's a combination of alternating side and factorial expressions. Doesn't really matter. What we're saying is that we think that correlation functions are sums over partitions. And partitions have the nice property that you can visualize them like this. So every diagram here is a partition, where I just draw a line between any points that occur together in a subset. And physicists will, of course, get excited about this because it looks sort of like interaction diagrams. But in this case, if you do the Möbius inversion, what you'll get is contributions of individual diagrams in terms of these correlation functions. So that's what you have here. So you do the Möbius inversion, use this weird expression, and you'll get, I've only shown like 3 terms here, but you can of course do it for any diagram. You get expression for their value in terms of a lot of correlation functions. Now, not just with plus or minus signs, but sometimes you get like factors of 2. The 4 point will have factors of 6 in there, which comes from this factorial. So it's like really non-trivial expressions you'll find here, but they're uniquely fixed as long as you say, I think correlation functions are made out of all possible processes. One exciting thing you might ask is actually, how does this look for quantum field theory, where we really care about diagrams, even more so than in sort of statistical physics? Well, you don't really have correlation functions because you don't have random variables. You have these Green's functions, which are expectation values in a certain state. And you can play the same game, except that your interpretation of these diagrams kind of changes. So you no longer think of these diagrams or these partitions as representing a certain process. They sort of are an infinite sum of internal processes. So you can still do this inversion, but I'm not sure how useful this is. I should speak to a quantum field theorist who knows if this is actually useful.
Does this relate to like Wick's theorem?
Well, I think Wick's theorem is what you use, which you can use it to motivate that partitions are reasonable.
Wick's theorem just gives you the partition.
It tells you what's inside here. It tells you what's inside of these shaded areas, I believe.
I'm not sure it was valid under general condition, or was it? Well, I don't remember. I know years ago.
I think if you want, so this is sort of, if you want to write out what one diagram means now, that's where you use Wick's theorem.
There's some loop, some type of diagram that are always zero, and then you end up with
Exactly.
diagrams.
Yeah, you can factorize everything into 2 points, and that's, I think, why you expect there to be sort of lines and loops in there. But don't ask me, ask a quantum field theorist. So the final example I want to show to really hammer down that this is sensible and established is from game theory and economics. So specifically coalitional game theory, where you say a set of players can come together to extract a certain payoff from a game. And crucially, some coalitions might be synergistic. Sometimes people work really well together, so they extract much more value than they could do individually. And to sort of capture this phenomenon, you say, well, the total value of a coalition S depends on the synergies of all sub-coalitions. Maybe there's little groups in a coalition that work really well together. Okay, I hope you get really bored by now, because again, we do the inversion, power set, alternating signs, blah, blah, blah. You get a definition of synergy. And those synergy things are kind of interesting because at the end of the day, after playing a game, a coalition has a big bag of money that they have to give out to all its members. So how do you fairly divide the payoff of a coalition? Maybe there's one player that you know is really valuable in a lot of these sub-coalitions, so they should probably get a bit more. And to do this, you use the Shapley value, which basically is using exactly this Möbius inversion of value, normalized, to pay out individual players. And sure, this is a very straightforward, simple thing, but here is Lloyd Shapley getting the Nobel Prize for this. So this originally was a highly non-trivial thing to say. Also, like his original equation looks a lot more complicated than this. But it turns out this is fully equivalent. So he beat me to it, but it's a sensible thing, at least. And in the paper I wrote about it, you look at many more examples. So this is a big overview of situations where I found exactly this pattern of people doing this secretly behind the scenes. And always they have some microscopic quantity that they decompose over Mereology to derive interactions or a microscopic theory. And if you look at these Mereologies, yeah, power set is very common, but you have other ones. You have partitions, you have anti-chains, ordered partitions. Chemistry has really fun Mereologies because you can look at partial orders defined by reaction networks, which are very specific, so they're not general Mereologies, which are more exciting, but have the disadvantage that combinatorics people didn't calculate the Möbius function yet for that. But individual molecules can have a Mereology associated to them. Yeah, so many situations, but I won't go into many of them because I will show now a bunch of new applications where I think, okay, now we've sort of established that this is sensible. Let's see if it's useful. Again, to recap, name of the game, choose a microscopic observable, choose a Mereology, derive the microscopic stuff. Let's start with information. So we'll now get back to, okay, we already saw that 2 Mereologies give you interaction information and total correlation. Can we do something more funky? And there's this idea that if you have a mutual information between two input variables and an output variable, then you could imagine that these variables, x1 and x2, carry information about y in 4 different ways. It can be uniquely in x1, uniquely in x2. It could be redundant between them, or it could be synergistic between them. Now, this is just some decomposition for 2 variables. You can do this more generally. And crucially, we're focused on the redundant part here, which says maybe y is the average of x1 and x2, let's say, or the OR gate, in which case, yeah, there's going to be a lot of redundant information here, and that's what we want to capture. And what kind of terms will appear in a sum of all possible redundancies among a set of variables? It's what are called anti-chains, which are incomparable subsets. And it's not immediately obvious why you should do that, but let's look at some examples of what anti-chains are. So some elements of the anti-chains on 3 elements are this one, the set that only contains the full set. We're going to interpret that as sort of the synergistic part carried by these 3. Then you have the set that contains all singleton sets, which is like the full redundancy among the 3 variables. But you could have something intermediate as well, where you say there's the set that contains x1 and x2, but also the singleton x3. And that's sort of an intermediate thing where you say, well, that's like a redundancy among a joint variable and an individual variable. And why I use words like synergy and redundancy here will become clear in a second.
It's like the levels if you do the complete.
Exactly. I think my next
different levels that you're.
I think my next slide has the picture of what it looks like.
Is it in some sense clear or trivial that this set of anti-chains forms the Mereology on your set?
It's not trivial.
Okay.
No, it's not trivial. I'll show some pictures, hopefully to convince you. I also have a proof. What's not an element of these anti-chains is the following, namely the set that contains x1 and x2 and x2. And the reason we want to exclude these is because what is a redundancy among x1 and x2 and x2? Well, that's just x2. Like that's obviously the redundant part between these. So we don't want to consider these. They're kind of trivial. Let's get rid of them. What you're left with is these anti-chains. This is not a new idea. This was already proposed 15 years ago and has been enormously popular since, to do this for 2 variables, or even 3. So this is what this Mereology looks like for 2 and 3 variables. You have the full synergy at the top, full redundancy at the bottom, and other stuff in between. For 2 variables, 3 variables, and 4 variables. So this is a Mereology that explodes very quickly. In fact, it explodes so quickly that nobody ever tried it beyond 3 variables. But you can do this, you can order them. Don't worry too much about the ordering, it's actually not so important, but this is what justifies the notion of redundancy and synergy. And then recently, for the first time, we were able to calculate the Möbius function on this Mereology. There was unknown, which is why nobody ever bothered going beyond 3. But now we know, it has a closed form solution. You don't have to worry what it is. It's again alternating signs, but the signs depend on ideals in a certain partial order generated by an anti-chain, something that you could calculate if you feel like it.
This is for general order.
But this is for general order in the sense like general number of elements, but always this anti-chain Mereology. Yeah. And once you know this Möbius function, now we're cooking with gas, you know, like now you can actually do this inversion because you know the value of this Möbius function. And this basically reduces to a matrix vector multiplication of this Möbius function and a bunch of mutual informations. And it turns out that this gives you a double exponential speed up in some cases, which is absurdly fast. So where this was possible for up to 3 variables, now we can do much more now.
But the question, of course, how long did it take you to compute the Möbius function?
Exactly. That took on my laptop about an hour. But the nice thing is, you can download it from my GitHub.
No, but also
I've calculated them for you, and they're super sparse. So I've spoken to some information theory software people, like this DIT people, and they might actually include this in their next version, just as a hard coded matrix.
The question before that is, how long did it take you to compute this function by hand, in the sense that it has this ideal structs.
Ah.
Yeah.
That didn't take so long because there's on isomorphic lattice, on isomorphic Mereology, people had calculated it. Nobody just knew how to instantiate the isomorphism. That's basically what I did, and then it was pretty easy.
But your conversion to 5 for 6 is too big to be true or to be
For 6, it's too big to store in a computer.
I see.
That's how quickly this Mereology explodes. But I still have the closed form solution. So you don't want to store the whole matrix, but if you're interested in a certain element, you can still calculate it very quickly.
Sorry, I lost track of it. So, why do you call this? Okay, so this combinatorial explosion is just that you have to do the sum over all possible
Anti-chains.
anti-chain
Yes.
sets, right? So that actually blows up.
Yeah.
But why do you say that this is then much faster? Because you still have this very huge matrix, right? You have this enormous
Right.
thing to sum over.
But before, people had to like do recursive sums over this. They first had to instantiate all elements. Searching for anti-chains is already non-trivial,
Yeah.
just to generate the set. Then they have to order them, which again is super exponential. So you just have super exponential upon super exponential, it just explodes. So we're still exponentially bad, but compared to double exponential, that's a double exponential speed up.
So your matrix is sparse.
Yeah.
So is there a way to just compute non-zero element?
Yeah.
Exactly. So you can store it very efficiently, and even if you look inside, there's a lot of Sierpinski triangles.
Yeah.
And the reason they're there is because they contain this partial order contains a lot of self-similar structures. You can exploit these to calculate them extremely fast without ever needing the matrix. In certain situations.
But is it self-similar or is for this example only?
No, that's generally true. I have proof of that.
But see if I want to read this matrix, so each line is one element you are ordering.
So here you see it. So this is the anti-chains. Here it's 0, 1, 0, 1, and 0, 1. And you just look at the two anti-chains and get the value of the Möbius function. And red is +1, blue is -1.
So to get my order, I would just need to sum lines on this matrix.
Yeah, it's a matrix vector multiplication indeed. But we can even do it faster than that if you don't want to bother with the whole matrix. There's a paper about this, specifically if you want to do more. Like one thing that we were able to do now is to decompose the different voices in Baroque music. And there's 4 voices, which means that they couldn't do this before, because 4 is more than 3. In fact, you want to follow them throughout time, so you do 4 plus 4, because you have them at 2 different time points. So you have 8 information carriers that you want to understand the information dynamics between them. You can sort of group this decomposition into chunks again. For example, if you notice that synergy goes to individual voices in terms of the information dynamics, then you can call that top-down causation, if you dare to speculate a bit. And what we did is we compared Bach, famously brilliant composer, with Corelli, about whom I'll say nothing. And it turns out that indeed, Bach, especially in these sort of harmonic constraints, like top-down causation or bottom-up causation, that's where Bach excels. Actually, none of the other ones. I don't want to go into too much detail. This is just to flex that we can do something that wasn't possible before. Next application, completely something different. Another macroscopic thing is the KL divergence, right? So you have 2 distributions, and they might be very high dimensional and differing in multiple ways, but this KL divergence just gives you a single number to tell you how different they are. So this is really, really something we want to disentangle. So same game again, take KL divergence, assume it's a sum over some kind of elements that I'll call delta this time. Do the Möbius inversion. And there's a slight problem here. We now have a KL divergence that's evaluated not on all variables, not on the whole support, but on a sort of a subset of variables. So what I assume here is that just means that it's the marginalized, the KL divergence between the marginalized distributions, which is, I think, sort of the most natural way to look at that. And then if this is meaningful, what I did here, then what these deltas should do is they should sort of disentangle this KL divergence. They should sort of tell you in which variables are these two distributions different. So let's do a test case. Obvious one, let's simulate an Ising model with random couplings up to 3rd order. Gaussian couplings, and that's what probability distribution P is. Boltzmann distribution for that model. In Q, what we're going to compare with, is going to be a copy of P, but we'll choose one of these random couplings and we'll start varying it. And see how these deltas respond. Are they able to pick up on exactly which coupling I'm varying in the Ising model? And it turns out they are. So this is varying the field, the 2-point coupling or the 3-point coupling. The variable varying is on the x-axis. And the y-axis is bits. So in black, that's the bits of the KL divergence and of a bunch of different deltas. And in each case, in red dashed, I've shown the delta of the coupling I'm varying. And you see that, yeah, in each of these cases, these deltas really do pick up on exactly what makes this KL divergence large. They almost perfectly reproduce it. And you see it gets a bit worse. Like there's some noise here. These are random couplings. I'm doing 100 iterations of it. But it seems quite robust. Like if you want to optimize some model and you only have finite compute to invest in optimizing different variables, this can tell you, okay, we really need to put all our effort and compute into doing backprop on these few variables and not bother with the rest, for example.
And this is actually identifying which of the parameters and variables are important for the.
That's right. So for example, this is saying actually it's only the marginal in the first variable where you're wrong. So don't bother with changing the marginals of the other variables. This is saying actually it's sort of the 2 points between variables 0 and 1. So maybe worry about the covariance between these. That's where you're wrong. It's actually not the marginals, right? The blue one, which is the marginal 0, doesn't contribute. So it's really only the joint distribution between these where you're wrong, whereas the marginals are correct. And this also works for third order.
How will these deltas all sum to the KL divergence?
Yeah, that's right. But I haven't shown them all here. Right?
That justifies your assumption with the marginalization.
No, they sort of sum by construction, right? What justifies that this is reasonable is that it does pick up on the right coupling here. That's kind of how I justify that this was a reasonable thing to do. I also don't think there's many alternatives here, to be honest.
And some deltas, they become negative. That's no problem.
There's no problem.
Because there's alternating signs.
Yeah. So it's not easy to interpret these deltas necessarily, but they clearly tell you where the discrepancy is.
So some deltas contribute negatively to the total KL divergence.
Yeah, they sort of compensate. So you were wrong in some variables, but your wrongness is compensated by other mistakes.
Can I ask you a quick question? So when you say that this DKL, I mean, do you have to recompute this for every subset? I mean, is that not
For every subset, like smaller than the one you're interested in.
But is that not extremely complicated or extremely?
I mean, for 3 variables, if you want to do it up to third order, like for these 3, that's 8 subsets.
Okay.
Actually, only 7 because the empty set is trivial.
But let's say for one 3-point interaction, for all 3 points, you will.
Yeah, that explodes quickly. So I'm not sure if this is like an efficient way to search. So I haven't implemented this. It's more of a show, okay, you can derive meaningful quantities with this. Whether they're efficient to calculate. Maybe in some problems, you already have a bunch of marginal probability distributions lying around in your process of calculating something else. Then you can sort of calculate this for free. If you have to calculate these marginals, that might be difficult. I don't know. So this is.
What goes with the polynomial with the number of interactions you have?
Exponential. So the size of the Boolean algebra, the power set Mereology on n variables has 2 to the n elements. Yeah.
No, I mean in your procedure, if you fix order 3, you get 8 per interactions, and then you get binomial any 3 interactions.
Right. Sure. Yeah. Okay.
So then it goes with
Yeah.
NQ plus times 8. So
yeah, it's not great, not horrible.
yeah,
Depends on how badly you want to calculate.
yeah. But for
So last example. Oh, sorry. Yeah,
no, it's for the trying to find the where to fix the interaction. It's kind of not so bad.
No, that's right. Yeah. Good. So now I'm moving again on to something completely different. Now let's look at interventional causality. So we're going to go back to this big Mereology, the complicated one, the anti-chains. The reason I like that one is because it captures this notion of redundancy and synergy really well. And maybe if I have causal effects, that's what I want to know. Like my causal variables, did they cause this output redundantly or synergistically or some combination of this? Another reasonable setting where you might disentangle into this particular Mereology. So we need some kind of macroscopic observable. And I want to look really at sort of interventional causality. So let's assume that we have access to a macroscopic measurement of do operators. We're able to like actually intervene in the system. And then what I call my big Q, my macroscopic observable, is the maximum average causal effect, which is the maximum causal power that X can have on Y. So I'm just going to do all possible interventions and see what's the biggest difference I can make in the output. Just because that's sort of a good way to summarize this. If my interventions are all binary, then this becomes quite simple, but I want to keep it a bit more general. Okay, let's decompose over this anti-chain Mereology. We now can do this because we have this Möbius function. One thing we have to do now, similar to this k divergence problem, we have the maximum average causal effect here of an anti-chain, not of a subset of variables. So we have to choose what that means. And one obvious thing to do is, well, sort of, I'm just going to take the minimum because that captures exactly this notion of redundancy we're after. Sort of what is the effect that I can have on Y with this subset as well as this subset. You can play with this and get different results, but this already led to quite reasonable results. Sort of a most basic starting point. So one test case you might sort of have intuition about causality and synergy is logic gates. I'm going to say we have sort of the logic gate, which the causal graph looks like a collider. I'm going to sample the inputs from binomial distributions. And the causal, that means that do operators are kind of conditional probabilities. It's kind of trivial causality, but that's okay. And I'm going to decompose it into these 4 logic gates. And or an XOR and copy, which is sort of a trivial logic gate. And let's go through them one by one. So OR. At very low probability, all the way on the left of the plot, then our inputs are almost always off. And we see that our causal power is almost always red, which is redundant. And that makes sense because the inputs are almost always off. So to affect the output, I just have to flip one on. It doesn't matter which one. So there's fully redundant causal power there. Whereas if you go to very high probability of the inputs, then the inputs are almost always on. So if I want to have any effect on the output, not only do I have to flip one down, I have to flip both down because it's an OR gate. So there you need synergistic causal power to affect the output. The opposite is true for AND, as you would expect. And for XOR it's quite interesting because at exactly p equals 0.5, you never really know what the input is. So to affect the output of an XOR gate, you have to have control over both. Whereas at very low probability or high probability, you basically reduce to an OR gate. So at least in this sort of super simple case, this really captures intuitively what you would expect. As sort of a dumb sensibility check, you can look at the copy gate, which just says Y is equal to X1. There you see, okay, clearly there, all causal power is unique to X1. There's nothing redundant, nothing synergistic, purely X1. So in this setting, it makes sense. You can look at something slightly more interesting, a chemical reaction network, but I'm going to choose a really boring one because I want things to be very easy. So I'm going to say we have some molecule Y that we're producing at our company, and Y can spontaneously emerge from X1 or X2, or it can be formed by combining X1 and X2. We have different rates. So you sort of get a steady state concentration of Y through this. And the intervention, the causal intervention that we mentioned, is like pouring a little bit of X1 or X2 into our reaction vat. We're still in trivial causality here, right? It's still a collider graph. So for actual causality people, it's not so interesting. For more interesting causality, there's a paper. But if already here, we see some really intuitive and good causal decomposition. So if K3, which is the combinatorial rate, is very, very low, then we see that almost all our power is unique to X1. And the reason that's true is because I set K1 to be much bigger than K2. So if we want to optimize our yield of Y, we best invest all our money into buying more X1, because pouring more X1 into our vat will maximize yield of Y. Now, if we're the regime where K3 starts growing, then the unique power of X1 goes down. And actually, it would make sense at very high K3, we really want to optimize adding both. We want synergistic causal control to maximize Y, because we can sort of get an effect multiplier because it's a combinatorial rate. So you really see how this causal decomposition of your system changes as you change this reaction rate.
But also the red one goes down.
Also redundant, yeah. So because it also means that even while fixing the other, by adding the first, you can already get a boost because they do multiply and are not zero. So adding one is good, but it's crucially, redundancy is symmetric. So here we had to buy a lot of X1 to maximize our yield. Here we know, it doesn't matter. If X2 is cheaper right now, we can also do that.
Suppose that you would actually suppress K1 and K2, then that red curve would go.
Yeah.
Okay.
Yeah.
Yeah. Okay.
So yeah, for non-trivial causal graphs, which I've done, you can look at the paper, or I have some extra slides if you're really interested. And now we come to the final slide, and this becomes more speculative. I hear the clock beaming 11, so that's good time, or 12. Let's look at renormalization. Because there's the observation that coarse graining a system is somehow a statement at the level of mereologies. It's sort of a change of your mereologies, but it's a very specific one. And I will argue that what it is, it's one half of a Galois connection. And I will have to define that. So a Galois connection is a property or relationship between two partial orders. It's between two posets P and Q. And to specify it, you have to give two functions. One from P to Q and one from Q to P. So you can go back and forth between these two posets. And they have to be monotone, these functions, with respect to the partial order. But not only that, there's this extra condition that when you compose these functions, on one side, you always end up above where you started, and on the other side, you always end up below where you started. Kind of ad hoc thing here to define. But I claim that these two functions form a Galois connection. So function one is rho, is our renormalization thing. It's basically a function that maps a part of our power set, a set, to that set with some variables removed. So you're like decimating, you're sort of removing some variables from your system. So that's why you're going to a smaller power set also. The other function, sigma, brings you back to your first, bigger one, but it does so by adding all of u to any element. Now, shown it visually here for where the first system we're looking at has 3 variables, and the second one has 2 variables. In green, I show rho, in red, sigma. Now, you can verify, if you look at all these lines, that these conditions always hold. Doesn't really matter. It just says, okay, we have a way to look at coarse graining as one half of the Galois connection. Now, why on earth is this useful to look at it like this? Well, there's a theorem by Rota from the 60s that says, let's assume we have a Galois connection between 2 partial orders, then actually that imposes a relationship on their Möbius functions. In particular, you can express one of the Möbius functions purely in terms of the other. And that's very useful for us, because if our Galois connection describes a coarse graining, then we can say, okay, well, renormalized interactions look like this, where we just do our standard procedure, but we have like a Möbius function of the renormalized mereology here. But we can substitute something purely in terms of our original mereology. So the whole way that this decomposition works in a new situation is fixed by how we started and how we define renormalization. Now, is this useful? I have one small example to sort of argue that it might be a sensible and useful thing to do, namely the one-dimensional Ising model, where we're going to decimate odd spins for every other spin. We'll write down our renormalized interactions. So our renormalized couplings are this Möbius inverse over the power set, as we saw previously in the Ising model example, of the macroscopic observable, where first this macroscopic observable was this energy. But now in the renormalized thing, we have to sort of say, okay, what do you have access to once you throw away the spins? We have access to marginalized probability distributions. So you do have to, by hand, say what the renormalized quantity is here. It's the log probability of the marginal probability, where you marginalize out all the decimated spins. And then actually the functional form of your renormalized couplings is fully fixed given the original Möbius function. So you don't have to come up with a new Möbius function or anything. It's fully fixed immediately. It has this form, which looks very similar because we're still in a power set world, basically. But it's okay, we now have an expression for our renormalized couplings in terms of a lot of probabilities. But we have said so little about the Ising model that we cannot get away with it yet. We have to impose sort of symmetries we expect there to be. For example, we say that doesn't matter which one is on, they should get the same, they have the same probability, which is imposing translational invariance. If two nearest neighbors are on, doesn't matter which ones they are. So you have another translation invariance input constraint. And if you further assume that there's no field, then you know that a bunch of other ones should also reduce to this number we'll call A for now. And actually, once you fix those, there's only one degree of freedom left. And you can just substitute in J equals log B, which we have from before renormalization. And then it turns out that this formula gives you exactly the renormalized Ising coupling of the one-dimensional Ising model. So this is correct. Like this has the right fixed points. This is without a field, actually, but you can turn on this field. You just have to impose some different symmetries, and you'll get the correct version here of the renormalized couplings of the one-dimensional Ising model with field. Correct fixed points and everything. So this works for 1D. I'm not sure if it works for 2D. But I found this already quite interesting, that this actually works in practice. And I never had to really do any summing over spins, because I'm assuming that what I have access to is just observations on the renormalized thing. So this is sort of implicit in reality if I would measure it. It's already done by nature for me. So I don't have to imagine what the Hamiltonian looks like. Just have to impose symmetries and the Galois connection theory.
What hinders it to apply to 2D?
I don't know, I've tried and I keep getting a wrong answer. I don't know yet what's going on. I might also not be doing it correctly yet. I'm trying to figure this out.
Or maybe you're right. You'll answer.
That's right. Yeah, it should work. I agree with you. It should work in 2D. And I want this expression for 2D. But I cannot even find the ground truth there. Like people do argue what the critical temperature is. But they do this through the Kramers-Wannier duality. On different, like triangular lattices, they have different arguments. They never write down this. So I don't even know what the ground truth is I should be aiming for, but you can sort of use this to imagine what the critical temperature must be. And so far, I haven't been able to nail it down. But absolutely, it's something I want to do. Like it seems obvious.
Maybe if you do it for 3D, you can solve the Ising model.
Exactly. This is my path to world domination.
The 3D is
Yeah.
no.
No, exactly. That's it will be exciting.
Okay, that's,
Yeah.
that's cool.
But I'll start with 2D.
But ask after.
Yeah. So to conclude, let's look back. So my main thesis here is that when you study a complex system, think about how the parts come together. Like think about Mereology. This might be a sensible thing to do. Because fixing the Mereology fixes the microscopic theory. And what I like about it particularly is that if you have a justification for your Mereology, then whatever interactions you derive from it sort of inherit this justification. So I've calculated a lot of higher order interactions among genes during my PhD. And invariably people would come to me saying, but is this real, this interaction? And like, I never know the answer. Like, what is a real interaction? I don't know, but if you can justify the Mereology, then you sort of have to accept that the interactions you derive are meaningful. They're the right ones, given your idea about how the world comes together. And what I like is that this sort of vague word, higher order, now has a precise meaning, because you have a partial order, and you can exactly say which term is higher than which others. So that was kind of clear in the power set Mereology. But for partitions, that wasn't always clear. And now you can say exactly which are the higher order ones, which are lower order. It's graded. With anti-chain ones, you can now say exactly what is higher order, what is lower. Like it makes this clear what it's meant. And there's some new applications. Like we have this double exponential speed up, which is nice. Can decompose causal effects in KL divergence. We can maybe do new renormalization calculations. I don't know yet if it generally works. And I'm sure there's much more. So some things I want to think about now is like, can we generate these Shapley values? Because game theorists and AI people actually seem to love them. Can I do the 2D Ising model? That would be fantastic.
Polymers.
Exactly. And one thing I'm currently thinking about, because I'm both at physics but also the ILLC, is there's a relationship between these anti-chains redundancy Mereology and classical logic. So there's a question, okay, what if you have quantum systems, what is sort of the proper way to think about the Mereology associated to that? No idea. Another fun thing I've only briefly explored, if you have a Mereology that is not only co-rooted but also rooted as a unique smallest element, then you can turn it upside down and you'll still have a Mereology. That's sort of a dual view of the world. So it gives you dual interactions. And those seem interesting. Like in information theory, they give you conditional mutual information. In Ising models, they give you sort of a different interaction in the context of all other spins being one. So it's really a dual view on interaction. And then finally, some of these Mereologies you can justify, like power sets. But maybe in some situations, you want to turn it around and say, I have an expectation of the microscopic theory, and I'm going to search through Mereologies to match that. Like maybe I want my final theory to have only low order interactions. And then you just search through Mereologies until you find one that actually does that for you. Which also, for example, you can say, I want a reductionistic theory. I don't want any emergent effects, like no higher order stuff at all. What is the way my system comes together? So yeah, my final claim is that this pattern is ubiquitous, it's insightful and useful. Thank you.
Thanks.
Good. How are we on time? Did I overstay my last? No.
10 minutes.
Quick question, the
Yeah.
normalization. I don't know much about this Galois function, but if you would imagine the normalization, the decimation would be union operation, like two sets merge after decimation, and how this Galois function relates to making every operational union or something like that. Intuitively, we would think as a decimation.
So I think decimation is exactly is exactly captured by this. Some of the other renormalizations I don't know. Like you have this majority rule stuff. I couldn't find an adjoint to that. Another half that makes it a Galois connection. So you mentioned linear operators or something?
I mean, in this case, you're out again. In this case, this diagram, so when you apply this Galois connection, you are actually making unions on the smaller sets to make
Here, yeah.
Oh.
This union. Yeah, so in one direction you remove U, and in the other you add U. But crucially, this is not a bijection, because A doesn't need to contain any of U, can only contain a part of U, and here you're adding all of U back. So for example, from the empty set, you remove U, so you go to the empty set, right? What is there to remove? Then if you go back here, you go to B, because we're decimating out B here. So it's not as simple as saying I'm going to either like project removing U or adding U. Like there's some kind of going back and forth there.
But does it mean that the inversion is exact or correct still? I mean, so I'm now confused again, because you said there's a one-to-one mapping between these two, the forward, backward.
Yeah, there's a relationship between Möbius.
And so it's still exact.
Yeah. Yeah, completely. So one thing you might notice actually is that this is not saying exactly one is expressed as a sum of the other. They're both sums. But they're sums under a certain condition. And it turns out that for like we know like coarse graining maps, one of these sums only contains a single element, which means that you can express one purely as a sum of the other, which is what happens here. That's also how Rota originally imagined this theorem to work. Right?
But is this in general the case for any coarse graining or for a particular coarse graining?
So I don't have a precise definition even of what counts as a coarse grading, but this is true for all coarse gradings of this type. So whenever rows of this form that it decimates out, it just removes certain variables from your system. And whenever this is true. But you have more complicated, you have these coarse gradings that say, well, I'm going to create new variables that are the average of a few, or maybe the XOR of a few. Like you could come up with all these different ones. And for these ones, you would have to check again, is there a right adjoint?
Okay. So
this
in that
is
sense, it's not so general. It's only about deletion.
yeah. So it's this decimation coarse grading. Exactly.
So if you want to make a general, you need a normalization connection and then the derivation with modulus.
Yeah, those are the two ingredients you need. You need a Galois connection that completes your renormalization with some other half, and you need the Möbius function before renormalization. Then it's fixed.
It to be always a Galois connection. There is a property to be named a Galois connection. It's just a connection that fulfills the normalization that you need.
So there are situations in which you can. There's other situations in which you could use this. Like if you know what the Mereology you're going towards is, like maybe you're going towards a partition Mereology where you know the Möbius function, then you don't need all of this, right? Then you can actually immediately calculate that. But my point is that so it doesn't have to be every other spin. You can do sort of a complicated renormalization where you choose exactly which ones you're removing. But it will still be a Galois connection. So yeah, it's general in that sense for all decimations, but not for all imagined coarse gradients. Because that seems like an infinite class of problems.
Yeah, so now I'm trying to see everything in the world in terms of different Mereologies. But
Very
I'm
good.
thinking about the Shapley value. So yeah, the Shapley value we're choosing a Mereology. But if I think back to my long time ago game theory, you get these different notions how to share a. Does it mean
That's right.
Are all these different notions related to different Mereologies?
Yes. So people have said, okay, maybe not all coalitions can come together to work. Maybe there's like a structure in your population where you have leaders that can assemble teams, but teams cannot come together without leaders. People have looked at that, and those, of course, like are sort of you take the full power set and you remove a lot of elements. Different Mereology, but doing this Möbius inversion on that Mereology gives you a new Shapley value that captures exactly what you're after. How to divide this payoff in the fairest way. That is still, so there's a few, it has to be efficient, this null player property, it has a bunch of properties, and they will satisfy that.
But you know the Möbius inversion for that?
No, not in general. No. So you'd have to actually look at your problem and think, is there a sort of an easy way to do this? Turns out there often is, because in the case where you take this particular one, where you still look at subsets under inclusion, as long as your ordering is inclusion, then your Mereology is guaranteed to be a distributive lattice, which is a particular kind of algebraic structure. And there's a theorem that calculates the Möbius function for all distributive lattices in a pretty easy way. So as long as you're still distributive, it's easy. I'm now imagining, what if you're not even distributive? Like, could you sort of have the most general version of Shapley values on any Mereology? Pretty hard. Because you also want it to be unique. Shapley value people want their value to be unique. And I'm currently working with Patrick Fauré on this, seeing can we still, under the most general setting, come up with a unique way to do this? And we're not sure it's possible. But it would be nice, because basically what this is saying is we have a lot of higher order structure, but we want to somehow project it down to the atoms again, to sort of the reductionistic elements. How do you do that best? And that's sort of a very general question to ask. So that's why AI people love this Shapley value, because they say, yeah, our very complicated model predicts some outcome, but which of the input variables was responsible for this? How do we assign all sort of synergistic effects that happen in all these layers? How do we go back to saying this was the important feature? And what they currently do is they just choose they calculate Shapley values for the input features and say, well, this one has the highest Shapley value. It must have contributed most. Because it gets the fairest, biggest payoff. So it's a general question. Like you want to project down all this higher order stuff again. And this is the best way to do it.
Something that relates to this, but slightly different. Like suppose I have, I have my macro observable. I just have it from a data set, and I'm trying to wonder, I want to model this or something. Can I use this framework to find the most informative way to divide my system into parts?
So I think you would have to say what you expect an informative decomposition to look like. Right. Like if you have some kind of way to quantify that, you could do it, right? And I think the space of all Mereologies is kind of frighteningly large.
Yeah.
All locally finite ones even. So you probably have to say, okay, I also expect my Mereology to be distributive or a lattice or like stuff like that. And I think a lattice is actually very reasonable. So all examples we looked at today are lattices, which are specific kinds of partial orders where any two elements have a unique smallest element above them and largest element below them. This kind of thing makes sense. Like we didn't have to specify to that to derive any of this, but I think you usually are in that setting where suddenly your space of Mereologies becomes much smaller. So there, yeah, I could imagine there being some class that you search through and you check each of the decompositions against some criterion. That gives you the right decomposition in a way.
Can I ask some stuff? Okay.
Okay, go ahead.
Clelia?
Yeah, I had a question about so when you do the inversion, it's quite computationally heavy, right? Because you want to calculate, like if you have n binary variable, for example, you need to calculate 2 to the n. Yeah, an inversion was the 2 to the n possibilities, right?
If you want all order interactions, yeah.
Yeah. But in the case of the Ising, the 0, 1 and the -1, 1, you can write this inversion as a Walsh-Hadamard transform. But because it's like in the -1, 1, it's a Fourier transform, and 0, 1 is like you can rewrite it down in the same shape. And I have the impression that maybe in some particular cases of the Mobius inversion, you should be able to write it down under that form as well. So the advantage of this is that you can use this fast Walsh-Hadamard transform, which is like what is used in fast Fourier transform. So then you can calculate it for, I don't know, 20, 25 variables in a few minutes. So maybe that could be something useful in some, I don't know,
so it's still exponential in the sense that you want to calculate them for an exponential number of couplings because they're just...
Yeah, but the calculation now becomes, it's not exponential anymore, the algorithm.
No,
so,
that would be fantastic. Yeah, absolutely. Yeah. So in all practical situations I've come across, you usually what I've started doing is calculate them from the bottom up. So I was doing this on gene expression data, for example. You start calculating 1 point, 2 point, 3 points, 4 points, and at one point you see all of them become 0 or indistinguishable from noise.
Yeah.
So you would have to have extremely good data to be bold enough to say, I'm going to calculate all orders of interactions. But yeah, it would be good to say, maybe you come across that situation, you want to be able to do that fast. Yeah.
One more speculative question is like, can geometry define an ordering let's say you have point clouds in distance, and they like it's up topological data analysis people first cluster the shorter points, like the closer points, and then you have an order based on the distance. Would you create an order like based on a function like a distance, and then make your Mereology on ordering, and then it be used for clustering and this kind of thing?
Yeah, let's think what that would mean, right? So you have like a partial order of pairs and their distance.
Yeah.
Then what you so again, so the theory that emergence from the decomposition inherits the meaning from the Mereology. So in this case, you would get sort of higher order terms. It would mean terms from more contributions from more distant points.
Yeah.
Yeah, so that's an interesting thing to do if you're interested in how local are my interactions.
You can do barycentric, like not pairs, like barycentric of any.
Right, exactly. Yeah. Yeah, you could quantify how interactions follow up with distance. The danger there is that if you're in like a real space, that your partial order collapses to a total order, because there's a very small probability that. So all distances are comparable, basically.
Yeah.
So you're not really in partial order world, you're in total order world. You can put them all on a line. In which case, the Möbius inversion theorem reduces to the fundamental theorem of calculus. So there's much easier things to do than this whole inversion business.
Even when you include the barycentric, not only the pairwise distance, but the barycentric.
That's just a real number. If your Mereology is based on real numbers, it's going to collapse very quickly to a total order. Yeah, which is why, like, you see a lot of the discrete structures like sets, partitions, anti-chains, lattices. They're all sort of discrete structures that really can have this partial order structure. Continuous structures are hard.
Maybe you can do some sort of filling.
Yeah, then you would be back to this. Yeah, absolutely. Yeah.
That's nice.
Thank you.